Welcome to the discussion on roles, skills, and customer interaction in business data analytics. In this session, we will explore the various roles individuals play in the field of data analytics, the essential skill required to excel in this domain, and the importance of effective customer interaction for successful data analytics project. Let's dive into the world business data analytics and understand how this aspect play a crucial role in driving insights and the value for organizations. The lecture outcome for this topic is first to get inspirations from nature and science and how their pattern was translated into model. Second, have a look on some typical model that being used in the current world. Third is to expose the student to fundamental of machine learning. And lastly, we will learn about different type of machine learning algorithm and their applications in the real life scenario. Let's take a moment to reflect on the honeycomb structure, a perfect example of efficiency in nature. The cell of honeybee comb start as circular shapes but naturally transform into hexagon as the comb is built. Why? Hexagons allow optimal space utilization, requiring less wax and maximizing honey storage capacity. This transformation is not random. It is a predictable outcome driven by the bee's instinctive understanding of space and efficiency. For example, retailers can predict customer buying behavior to optimize inventory, just like bees optimize their storage. Similarly, healthcare providers can use predictive models to anticipate patient needs, improving outcomes and resource allocation. Just as the hexagon maximizes space and efficiency, predictive analytics maximize the value derived from data, allowing organizations to anticipate future trends, optimize resources, and also make better decisions. Now, let's take a look on predictive analytics and the Earth-shaped model. The Earth shape is nearly spherical due to gravity pulling equally in all directions. However, it is not a perfect sphere. The rotational force causes the equator to bulge slightly, stretching the Earth into the oblate spheroid. This balance between gravity and rotation creates a predictable and optimized structure. Just as the Earth shape is influenced by force like gravity and rotation, predictive analytics operate by balancing different data forces, historical trends, patterns, and variables. Summary: both the Earth shape and predictive analytics exemplify the power of balancing forces to achieve optimized, predictive outcomes. The Fibonacci sequence is a fascinating pattern found in nature where each number is the sum of the two preceding ones, such as 1, 1, 2, 3, 5, and so on. This sequence appears in plant leaf arrangement, ensuring optimal packing and maximizing sun exposure. Predictive analytics, we see a similar concept, which is finding patterns in data to optimize outcome. Just as the Fibonacci sequence helps plants efficiently use space and resources, predictive analytics enable organizations to uncover patterns and make data-driven decisions to optimize performance. Now let's move to the next slide. So what is machine learning? Machine learning is both a science and art focused on programming computers to learn from data. It allows systems to improve their performance on specific tasks without being explicitly programmed for each scenario. As Arthur Samuel stated in 1959, machine learning is the field that enables computers to learn from experience. This means that a computer program can enhance its performance on a task, let us call its task T, by learning from past experience, which is experience E, and measuring its success through a performance metric, performance measure P. In conclusion, the more data and experience a machine learning model has, the better it becomes at making predictions or decisions. This foundational concept is what drives the development of intelligent systems across various applications today. These are some examples of machine learning applications. First is to analyze image product on production line to automatically classify them, defects or non-defect, detecting tumors in brain scan, automatically classifying news articles, automatically flagging offensive comments on discussion forums, summarizing long documents automatically, creating chatbots, forecasting company revenues, and many others. There are 4 types of machine learning. First is supervised learning. Second is unsupervised learning. Third is semi-supervised learning. Fourth is reinforced learning. Let's take a look at all these types of machine learning one by one on the next slide. What is supervised learning? In supervised learning, the algorithm is trained on a labeled dataset, meaning that each training example is paired with an output label. For example, a common application is a spam filter, which is trained on the datasets of email labeled as spam or not spam. The model learns to classify new email based on this training. As shown in figure 1.5, in this example, the training set consists of emails labeled as either spam or not spam. The model learns the pattern and features of this labeled email, such as specific keywords or sender details. When a new email arrives, the trained model applies its learned pattern to predict whether the email is spam or not. This is how many email systems automatically filter out unwanted messages, saving time and improving user experience. In a sense, supervised learning bridges past data with future predictions, turning historical patterns into actionable insights. Some of the most important supervised learning algorithms are k-nearest neighbor, linear regression, logistic regression, support vector machines, decision trees and random forests, and lastly, neural networks. Next is unsupervised learning. The unsupervised learning involves training an algorithm on data without label responses. The model tries to learn the underlying structure of data. Imagine you have a lot of data about your blog's visitors, such as their activities time and preferences, but no label indicating their specific categories. Using unsupervised learning, a clustering algorithm analyzes this data to group visitors with similar characteristics. For instance, it might identify that 40% of visitors are males who enjoy comic books and browse in the evening, while another 20% are young sci-fi enthusiasts who visit during weekend. Unlike supervised learning, you don't tell the algorithm what patterns to look for. It discovers them on its own. This makes unsupervised learning invaluable for uncovering hidden insights, such as market segmentation or user behavior, which businesses can use to tailor strategies. This slide shows the examples of unsupervised learning model. First is clustering. Second is anomaly detection and novelty detection. Third is visualizations and dimensionality reduction. And lastly is association using rule learning. What is semi-supervised learning? Semi-supervised learning is an approach which combines both labeled and unlabeled datasets for training. It is particularly useful when acquiring a fully labeled dataset is expensive or time-consuming. For example, in an image classification, a model might be trained on a small number of labeled images, for example cats and dogs, and a larger set of unlabeled images. This helps improve accuracy by leveraging the unlabeled data. One prominent example of a semi-supervised learning algorithm is the Deep Belief Network, which is DBN. DBN are composed of multiple layers of stochastic latent variables. They are built using unsupervised components known as restricted Boltzmann machines, which is RBMs, which are stacked on top one another. How does this work? The initial layers of the DBN are trained in unsupervised manners using the unlabeled data to learn the underlying structure and features of data. Once the unsupervised training is complete, the model can then be fine-tuned using the labeled data, allowing it to make more accurate predictions. Semi-supervised learning is particularly beneficial in the fields like image recognition, natural language processing, and bioinformatics, where labeled data can be scarce but unlabeled data is abundant. In this slide, we focus on the concept of reinforcement learning, which is a distinct area of machine learning that emphasizes learning through interaction with an environment. Reinforcement learning is a type of machine learning where an agent learns to make decisions by taking actions in an environment to maximize cumulative rewards over time. Unlike supervised learning, where the model learns from labeled data, RL relies on the agent's experience and feedback from the environment. The agent learns through trial and error, exploring different actions and observing the results. Over time, it develops a policy that defines the best action to take in each state to achieve the highest cumulative rewards. Examples of applications that use reinforcement learning are game playing, robotics, autonomous vehicles, and personalized recommendations. The 7 steps of machine learning outline a structured approach to developing machine learning models. Here is a breakdown of each step. First is data collection. This step is to gather data relevant to the problem you want to solve. This data can come from various sources, including database, online repositories, or through direct collection method. The quantity and quality of the data collected significantly influence the accuracy and performance of the model. Next is data preparations. Data preparation is to clean and pre-process the data to make it suitable for analysis. This includes handling missing values, removing duplicates, and transforming data types. Proper data preparation ensures that the model learns from high-quality data, which is crucial for achieving reliable results. The third step is model selection. Model selection is to choose the appropriate machine learning algorithm based on the problem types, for example, classifications or regressions, and the nature of data. The right model selection is critical for achieving optimal performance and accuracy of your results. The next step is model training. Model training is to train the selected model using the prepared dataset. This involves feeding the model the training data and allowing it to learn the underlying patterns. Effective training is essential for model to make accurate predictions on unseen data. Evaluating the model is a crucial step in a machine learning process, as it determines how well the model performs on data it has not seen before. This step helps ensure that the model is not only accurate but also generalizes well to new, unseen data. The primary goal of this step is to measure the model performance objectively using various metrics. This helps in understanding how well the model is likely to perform in real-world applications. Also, evaluating the models on unseen data allows practitioners to assess how well the model generalizes beyond the training set. Next step is parameter tuning, which is often referred to as hyperparameter tuning, is a crucial step in machine learning workflow that focuses on optimizing the setting of a model to enhance its performance. Hyperparameters are the configuration settings used to control the learning process of machine learning model. Unlike model parameters, which are learned from the training data, hyperparameters are set before the training begins and can significantly influence the model performance. The choice of hyperparameters can greatly affect the accuracy, speed, and generalization ability of the model. And also, hyperparameter helps in controlling the complexity of the model. For instance, a model that is too complex may overfit the training data, while a model that is too simple may be underfit. The final step in the machine learning workflow involves using trained model to make predictions on a new, unseen data. This step is crucial for evaluating the model's performance and understanding how it will behave in real-world scenarios. The primary goal of this step is to assess how well the model generalizes to data it has not encountered using training. This is done by using the separate test set that was withheld from the model during the training and validation phases. By making predictions on the test set, practitioners can gain insights into how the model will perform when deployed in real-world applications, where it will encounter new datasets. In summary, we have learned the 4 types of machine learning, which are supervised learning, unsupervised learning, semi-supervised learning, and also reinforcement learning. Each play a crucial role in how we harness the data to create intelligent systems. Thank you for your attention, and let's continue to explore the exciting landscape of machine learning in our next class. Bye!